this problem, there are two identical circular wire loops which are placed in parallel planes. So these are two current carrying rings which are placed in parallel planes. So maybe let's say in the XZ plane. Now both the rings are kept fixed by some external agent, and they have made a hypothetical plane which is exactly midway between the two rings, right? And the point O here represents the center of the line connecting the centers of the two rings. So this is the bisector of the line C1, C2. There is no gravity in this problem and both the rings are fixed. The question is somewhat like this, that if an external agent throws an electron from the center O with some velocity V0 rightward, and it keeps on moving on some path not known in the plane, in this plane, I don't know what happens, you have to analyze. But the question was that what can be said about the electron's speed and direction when it is very far away from the loops, and the appropriate logic for that. What can we say about the magnitude and the direction of velocity of the electron when it is very far away from the center? Yeah. So basically, if I look into the context of the problem talks about analysis of magnetic force on this electron in the magnetic field of two current carrying loops. As the problem is not having any gravity, so there is no hassle for that. ठीक है, बाकी सब कुछ problem में mention है. So now we need to think about the problem. Now, when this particle will move, this electron will move on some general path. Let me start from the scratch. General baat karte hain. I don't know what is the curve that it will follow. So just according to the question, there is some curve it will follow. It will reach some point, and I want to analyze this problem in the r theta coordinate system in this plane only, the central plane. ठीक है? तो एक काम करते हैं. Let's say the particle is here at a general point. I want to see the rate of change of angular momentum of this particle, and be very careful about the expression I want to write. If this guy is at a general position, I want to observe the rate of change of angular momentum of this particle, and that should contribute to the torque acting on the particle. This is the crux of this problem. Just try to write all the terms carefully. I'll put the signs appropriately. So I thought when it will be at a general R. Now, anybody under any confusion can always look into the top view. So if you observe the top view, you will see this point O, see some general curve. Or obviously baat hai ki when the guy will be at general R and theta, it will have a VR velocity, it will have a V theta velocity. That's what I said. Whatever curve it is following, don't worry. But general velocity will have two components, dr by dt and r d theta by dt. VR and V theta. Now my point is, the angular momentum of this particle is provided by V theta, V tangential, right? So you should say this is m V theta into r. Remember, this is general R, general V theta. Because your radial component of velocity hai, that cannot provide any angular momentum. And the second thing is torque. Now, the torque is provided by, now one thing that we should be clear about while writing the solution is, a person can say, sir, how are we convinced that this will lie in the same plane? Now, there is one standard point I'll mention here. I'll prove this thing that these two rings will produce magnetic field by Biot-Savart law only in a direction which is normal to that central plane. I don't know the magnitude, but I am absolutely convinced, I'll prove it, that the direction of magnetic field should be perpendicular to that intermediate plane everywhere. Now just understand, if I prove that the direction of magnetic field everywhere is perpendicular to that plane, then you are convinced that if I provide a flick in the plane, whatever be the function of magnetic field, it cannot go out of the plane. I don't know the magnitude. I'm not commenting on magnitude. I'm commenting on the direction. Right? So let me just prove it. How will I justify this? For proving this, what I will do, you have got a ring above, you have got a ring below. You fragment the big ring into a grid of circular loops. Fill it with a grid. So जो ऊपर वाला ring है, I think all of you understand what when I say fill it with grid. So that's what I'm talking about. The thing is, I'll segment it into multiple wires, multiple radial lines. So I will have this small current carrying loop, small current carrying loop. You understand? Ultimately, you will only have a loop which is outside, the basic funda. बीच वाले सारे cancel हो जाएंगे. Now, all these small loops, now by symmetry of the problem, if I have got a loop somewhere here, if this guy has got a current of I will have a hypothetical loop here having current of I. So I will have a loop downside also having current of I, and all these intermediate loops will cancel out. So basically, I've got two loops. Now tell me, if in 3 dimension I have a loop somewhere, so it will have a magnetic moment perpendicular to the plane. So his friend downside will also have the same magnetic moment. So basically, everything can be broken into two magnetic moments. The complete ring above, I don't want to put it as a single magnetic moment. That's not right, because uska position sabka alag hai. So I will make small loops everywhere, every loop and his counter loop downside. His magnetic moment, his friend's magnetic moment. So basically, this structure can be broken into 2 equal magnetic moments, and 2 का सेट बहुत सारा बनेगा. तो उस बीच वाले प्लेन में आप कहीं भी चले जाओ, forget this. So basically for you the question is, if I have got a magnetic dipole moment, I have a magnetic dipole moment, and I am lying on the perpendicular bisector at this point, what is the direction of magnetic field? तो magnetic dipole की तरह देखो, like electric dipole. So if this is your dipole moment here, and this is a dipole moment here, symmetric, perpendicular bisector, I have to write the field here, direction of it. And tell me, if I resolve it into, I mean, all of us are clear, if I resolve into the radial component, resolve his friend also into radial, this guy will provide me a field here, this guy will provide me a field here. So these two guys will have a field upward. This is answer. One component. Now separately, I'll look into this component and this component. So basically, I'll draw the diagram separately. I'll have a field here, I mean, dipole moment here. So the magnetic dipole moment will have a magnetic field which is NT to this guy, like this. And the guy who is there downside, why I'm drawing it separately, because people confuse from these lines. That is separate, this is separate. So if you draw a dipole moment here, and I have a point here, I'll have a magnetic field like this, which is normal. So this vector and this vector, these two vectors will also have a resultant downward, and those two upward. So net can only be vertical. I don't know up or down, but it is vertical. So let me go back to the question. That means at this point, the field is either up or down, whatever it is, call it B. Some B as function of R. Up or down, I don't know. I've treated something. At least you are now convinced that the plane of this motion will be the same. QV cross B will always ensure that this electron lies in the same plane. It cannot come out of plane, right? And the speed also can't change because magnetic force can't do any work. So V0 will remain the same. I don't know the direction, but V0 to rahega. So on the left hand side, now I want to write torque. So torque should be R cross F Now I want to write force. Now tell me, you have two forces of V cross B. One is because of the radial velocity, but that force will be along the tangent and that will provide the torque. So you got it. It's like R, lever arm, into force. And that force is E ka mod VR into BR. B as function of R. जो वेलोसिटी का रेडियल कंपोनेंट है वो मैग्नेटिक फील्ड से इंटरेक्ट करेगा. इट विल जनरेट अ फोर्स which is tangential to R, normal to R, and that can provide torque. But the force which is generated because of the tangential component, this guy, will be along the radius, but that cannot provide torque. So that's why I'm not written. And try to understand, there may be plus or minus. I'm not interested because you will understand effective equation won't require that. There may be an effective plus or minus. Keep it. I'm not interested right now. Answer doesn't depend upon that. So the main thing I have written, these are components. They may have some sign. Stay with that. Don't worry. Cross multiply this by dt. You understand that VR, velocity radial, is actually dr by dt. And I want to cancel out dt from both the sides. Now what I got is plus or minus, leave it, R, E, B as function of R, dr is equal to d of mass m r v theta. That's what we got. Rate of change of angular momentum is this. यहाँ तो पहुंच गए. Now, this equation on the left hand side is talking about the, because of symmetry of this problem, if I multiply this problem by 2 pi and I divide this problem by 2 pi, just observe that 2 pi r dr into br is basically plus minus E upon 2 pi into d phi, differential magnetic flux. इस plane में you are sitting at this R. This is the R from here. And because of the radial symmetry, whatever B you will have here on that circular ring radius R, you will have the same B everywhere. The theta symmetry of the rings, field to ring ने produce किया. So if I go to R and I cut a differential ring of dr, the flux is field into area. B is normal into area. It may be plus minus. So plus minus may change, but it is d phi. As far as, so effectively I have E by 2 pi d phi is equal to d of m into r into v theta term. M into r into v theta term. And now we are absolutely close to the final result. Now, I will take a sigma or an integral of this equation. I want to put this equation into initial to final mode, the start to end. So try to understand one thing. That if you integrate this equation, take integral both sides. So what we are getting is plus minus E upon 2 pi, the total flux delta phi term, plus minus is still there, is a delta of m into r into v theta. And now my final statement is, by the time you will come out, you will go up to infinity, whatever path you follow. So once you will keep on, because he said very categorically, when he is very far from the loops. So when he is very far from the loop, he has indirectly covered up distances up to infinity on that plane. Once he is done with that, the total magnetic flux of both the rings through this intermediate plane should be zero. बच्चा कह सकता है कि sir, how come is he covering flux? He was not covering. He was covering only R, BR, DR. But I deliberately multiplied by 2 pi or 2 pi. So I apparently converted this equation into something where whenever he was crossing, physically he was crossing dr. So in my mind, I was crossing 2 pi r dr because I had that r b as function of r into dr. So just by multiplying it by a constant, it felt that he is covering all the rings. तो जहां से वो dr निकलता था, mathematically the flux was involved there just by multiplying the constant. So flux, 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 and there's a property: magnetic field lines form closed loops. So whatever field is coming here, whatever line is coming here, somewhere up to infinity, it has to cross that again. So number of lines crossing that intermediate plane, hypothetical plane, will be the same. Whosoever will cross down has to come up because it forms a closed loop, whatever angle it is. So the net contribution in the flux is 0. So this term becomes 0 when that guy reaches infinity. That tells me m is already a constant, that delta of this term is 0. And delta of this term is 0 tells me that the velocity, my answer now is, in the final state, the guy will have v0 speed only, v0 only, in the radial direction. In the radial direction. Try to understand how come I have made this statement. If the velocity would not have been in the radial direction, it will have a tangential component, then this term will have a change. Because initially r was 0. Initially this term was 0. So finally also this term can be 0, should be 0. But at high r, if I have any velocity which has got a tangential component, then this term finally will not be 0. But I need this term to be 0. So the answer to the question is, at infinity, that charge will be moving radially. So he will be, the charge, electronic charge, will move with v0 speed. That is simple, because there is no work done by magnetic forces on the charged particle, whatever be the field. But उसके पास कोई direction का change नहीं हो सकता. This is a beautiful problem written in 200 more puzzling. And if you don't observe it in a proper way, then it is different. And the best idea in the problem is about the flux. And as a student, that you have to think about this, that we have to write an equation, not straightforward, because I have written those equations which help you getting the solution. But to think on those lines, speed will remain v0 very obvious, but direction at that stage comes from this idea. Let's move on to the next problem. Yep. Flux वाली बात फिर से बोल देता हूँ. While it crosses r to dr, d phi that I am talking about is the change in the flux across any ring 2 pi r dr. Actually, he is not crossing 2 pi r dr, he is crossing dr only. But a compensation of constants, I am thinking that whatever he crosses the complete area. I am shading that area completely while this charge particle is going upwards. Then everything falls in. The second problem for the day. Now again, this problem we want to solve by the geometry. There is a analytical way of solving which I don't want to use. Question क्या था? That there is a regular tetrahedron, and from these 2 points you are supplying some current, you are taking out that current I, and the point which is the center of this regular tetrahedron, we are interested in finding out the magnetic field at that point. Let me first do the simple thing, then we will solve it carefully. Already he said that the wires in which the current is coming and leaving, their line of action is towards the center point, center of the tetrahedron, right? ठीक है, तो उनका तो कोई magnetic field आएगा नहीं, White-Savart law. So magnetic field here will be only because of the currents in the edges. I've got those 6 edges, so I will have current in those edges and appropriately. Obviously, all of us do understand that, I mean, very simple idea, that this structure is somewhat like this: A, B term C, and the top edge is somewhere here. So by Kirchhoff's, Wheatstone and all, you understand that if I supply I and take out I, there won't be any current in this guy. And rest is simple. क्योंकि 2R है. So, I by 2 will come here. I by 2 in this total, so it is I by 4, nothing there, I by 4 here, and I by 4 here. Now comes the actual problem. How will we write the magnetic field at the center of the tetrahedron? To this point, I just use that simple property that this guy is balanced, 2R, equal, and everything. Now, so just be careful about the geometry that we want to use here. And I will try to write magnetic field one by one for all the elements. Now, again, there are two ways of looking into the problem. By the absolute exact geometry of the problem, we can write the exact B vectors and solve. But by a bit of symmetry, things can ease out. You write magnetic field because of those edges one by one. Let me see. Just try to write the expression one by one. So AB current I have taken as I by 2, AC I by 4, CB, ठीक है, AD area. So I'll write because of AC. Because of AC. Now I'm using this fact that the direction of magnetic field because of current in AC is along dB cap, and whatever is the magnitude of field at the center because of AC is having a current of I by 4, is the current, because by itself along with your magnetic field that is directly proportional to current. Yeah, and all the terms are geometry terms, 3D geometry terms, ZL cross R, they are only geometry. So those geometry terms I'm treating as constant K, some K, I don't know, are not required. So my statement is, the only thing I was interested in is जब मैं current लेके जाऊंगा A to C में, and I want to write field, just think of a equilateral triangle on the base of this room, and try to drive some current through your right thumb along the line AC, C point is backward, right? And try to write the field at the center of the tetrahedron. I think all of us understand that property. If I hold this AC at the center and I want to write the field at the center of tetrahedron, I will have a plane in which one edge is AC, the second face is the face connecting AC with O. Here it is kind of difficult, but you understand that plane. And now I'll use the direct property. The normal to this plane is parallel to the edge dB. This property of regular tetrahedron I'm using. इसका जो normal है वो that edge, opposite edge from top, it is parallel to that, and that was dB cap. I just used the right hand thumb rule to find the direction. Now, one thing is very clear, with respect to every edge, the relative geometry with respect to center remains the same. So every guy, AC, CB, whatever I will write, the constant will remain the same, only the current term will change and the direction will change. So let me just write those terms. You also write your terms. Let me see what is coming up. I've written it, so I'll write CB. CB comes at K into I by 4 into DA cap. Check. CB का आ जाएगा DA cap, because direction of current is along C to B. So DA cap. Then I want to write AB. AB is coming out as CD cap. नीचे है ना? AB का ऊपर आ रहा है CD cap. And this guy is K into I by 2. Current there is I by 2. Using those properties. Then I'm writing AD. AD is coming out as BC cap AD आ रहा है BC cap, and here also it is K into what was AD. D was I by 4, so KI by 4. ये आ गया. कौन अब बच रहा है? DB. Only these 5 people are there. So DB direction, what are we getting? AC cap. Yeah. Check कर लो. AC cap आ रहा है. K is there in DB, and what is the current in DB? DB is I by 4. So finally, when I have to write the field because of these 5 people, K was common, I by 4 was common. I got terms like DB cap plus DA cap plus 2 CD cap plus CD cap plus BC cap plus AC cap. That's what we got. And now few things we will check, like DB cap plus BC cap is DC cap. हाँ तो एक CD cap तो गया, ये DC cap है. And DA plus AC, DA cap plus is DC. These two guys are also DC cap. So I think you understand, 2 DC cap or 2 CD cap will cancel out, the field comes out to be. So the more important thing is the geometry of the problem. And you need not write all the terms specifically, just use the relative geometry with respect to that point. In such 3D systems must be some pattern. Obviously, he's not expecting us to write all the functions in I, J, K and solve. So otherwise, it will take 5, 6, 7, 10 minutes to solve. Although from basic also, you know all the coordinates, we can write all the fields, but that is not the right way of approaching. Let me show you one more problem of B based on 3D geometry. Take this problem. Here I'll use the ideas of superposition and 3D geometry to explain the result. And a bit of Ampere's circuital law also. So read it carefully. What is the problem like? Problem says that the surface of a plastic globe of radius capital R is uniformly covered with a conducting material, and that conducting material has some material, graphite layer, whatever. Now this plastic globe is placed on an insulating support on the table. One end of a long, straight, radial current-carrying metal wire. So this is that long, straight, current-carrying metal wire. Stay patient with the problem. There are a lot of ideas like solid angle, everything I will use. It's a combination of all the ideas. So wire aaya seedha. Then from the surface, the current can flow on the surface in some manner, but this guy extracted the current from this point I, again up to infinity, infinity, these are infinite. This is the flow, and the material inside is insulated. Now his question is, if you look into this latitude here, which is the bisector of the first quadrant or octant, right, this point, 45 degree, and 3D it is actually a ring. And this point he wants to take just outside. He is very clear. What kind of magnetic field is present inside, outside? His interest is, obviously somebody who can solve this knows everything, which will be explained. Not only this, in a multi-correct, he can ask magnetic field anywhere. I can write magnetic field anywhere. I'll write it, don't worry. So his question was, can you find out the magnetic field strength at the point P halfway between the input and the output junctions of the current and just a whisker above the globe's surface? Just a whisker above, so thoda sa bahar. How can we write the magnetic field here? Now, obviously, in this problem, he is not expecting us to cut this into semicircular rings or quarter rings and integrate and all those ideas. They are not relevant. So let me use a conceptual idea. First thing in this problem is, I'll break this problem by principle of superposition into 2 different current models first. And what superposition I will use? First of all, I'll say I'll bring in current from infinity. I won't let it out here. So what will happen here is the current aata hai and make it a conducting hypothetically, because after I will overlap, it will all cancel. Now, so current is coming, and then from the center, I mean, it is diverging outwards, right? So ऐसा लग रहा है कि it is coming from a tip. Something is coming, given to the system, and think of this current to come out in a conducting. Think like conducting three-dimensional space. Let the current move out. Because everywhere, when you will think of, I'll cancel it, don't worry. This is three-dimensionally, spherically symmetric flow of current. Three-dimensionally symmetric flow of current outwards from diverging from the center. And what I want to superpose it with, this is my first thing. And my second body, which I want to superpose it with, is this solid sphere, the current coming out from here, I. And now I want to bring in everything from outside, and I want to extract it like this. So just stay intact, the problem, right? So it is coming from infinity, convergent towards the center, and then it comes out. And just add these two combinations, so you will get the original flow of current. So nothing will stay outside. This was just a hypothetical way of explaining the same. Now, just try to write the expression of magnetic field. मैंने एक जगह नहीं बनाया, but now I'm ready with this point that if there is a general point somewhere in three-dimensional space outside the sphere, can we write the function of magnetic field at that point? Just try to write the magnetic field function at that point. I haven't said anything about the current inside, not required, but outside current, whatever I have done, that I have cancelled. So now I want to write B at a point which is, now just stay patient here. Agar I draw a line which is at a distance of small r from the center, general point, and with respect to this vertical, it is at an angle of theta. Remember, this is I want to think of this point as a cone kind of structure like this, right? This is r, this is also theta. I want to derive B at this general point. I don't know, but maybe as a function of r theta with the appropriate direction. Now comes the utility of breaking this problem in these two configurations. I will write it one by one, and we will use Ampere's circuital law. So let me just draw this point here. Let me take this ring as my Amperian loop, right? The ring that I have drawn. This I want to take as my Amperian loop. I want to write the magnetic field. One thing I know, and take it one by one now. Just draw this system which you can see right now and try to write the field here. So on this, similar to Gauss law, on this Amperian loop, my first statement is if the field is like tangentially coming out. Honestly, I've drawn that tangent, but I knew that if it is coming out, it is having some value B. So ये तो clear है by theta symmetry that this B on that ring is the same. So I knew that if I also move in this direction also, and I take the line integral of B dot dl, तो B का पूरे loop के ऊपर integral आ जाएगा, B is constant. So LHS will become B into 2 pi into, so if if this is theta, this is small r, this radius here comes out as small r sine theta. So B into 2 pi small r sine theta is what I am getting. Now comes the bigger problem of writing the enclosed current. Now comes the issue of writing the enclosed current there. So 2 pi small r sine theta B. B is some, right? I mean, we are writing B as some function of r theta. Now, what about the enclosed current? The current which is going down is supporting the curl of B. So that is positive I. So this yellow current vertical is giving me a plus I. But then these orange currents are coming out. So I'll have a orange negative term, and that current I will write by the concept of solid angle. I knew that this minus term will be minus of I divided by a solid angle of 4 pi, and I am inside inside a cone which is having a solid angle of 2 pi into 1 minus cos theta. So I upon 4 pi into 2 pi into 1 minus cos theta, 1 minus cos theta. This is the term you will write. So basically, what we have written is B into 2 pi small r sine theta in that case is mu naught into capital I into 1 minus 1 upon 2 into 1 minus cos theta term, 1 minus cos theta term. So, I mean, you will have mu naught I एक factor of 2 आ जाएगा और क्या मिलेगा आपको 1/2 plus 1/2 cos theta. So 1 plus cos theta term, 1 plus cos theta term. Keep it as such. So mu naught into I by 2 into 1 plus cos theta. And now your B this B that I have written here, just because of the first situation, this is not the result, but this B is mu naught capital I by 2 into 2 pi r sine theta into 2 pi small r sine theta into 1 plus cos theta. Now tell me, if I was just solving this problem in advanced, as far as the answer to the question is concerned, now I'm ready with my answer. Because वो point उसने बड़ा अच्छा दिया है. So it is absolutely symmetric. If I sit here and I say there is some B here, because at this point small r will be equal to capital R and theta is 45. So I'll have some field coming out. And if I sit here, now again I observe, now because I am, with respect to this wire, I'm on the left hand side, here I was on the right hand side. So the complete symmetry changed. So अगर यहाँ बाहर आ रहा है, तो on this side again it will come. Getting a point? मतलब, if I'm standing vertically, I was on the right side of this wire which is coming down. But I'm sitting like this, I'm on the left side of the wire, but the current is out. So the complete current orientation is opposite, but I am also on the opposite side. So it will support. So my answer to the question is twice off at that respective point. Now the effect of one guy, so let me by 4 pi capital R sine 45, 1 by root 2, and numerator is 1 plus cos theta. So 1 plus 1 upon root 2 will come again in the result, right? Now I think everything should be here. It should be mu naught I upon 2 pi R, and it is a factor of root 2 plus 1. Just check this. It should be mu naught I upon 2 pi R, and the result is root 2. So this is actually the final answer to the question. That location is easy, so we are not interested. But you got this point that if you can write field because of this here, you can write field at any point outside because of anyone. वो तो आसान point था, so I directly wrote it. Otherwise, I would have written. Just a bit of directional symmetry I need to understand. Right? So Ampere's circuital law and solid angle concept is there. Other than that, we have used the fundamental geometry. Any, like, even if you want to talk about the direction, somebody can say, okay, you have taken B dot dl, but you knew the, how do you, I knew the direction of B. That is something which you have to find out from Biot-Savart also, either by symmetry or by Biot-Savart. You should be clear that if I have a lot of spherically symmetric, if I have equal current carrying wires diverging from this point, from the center of a sphere, then at any point in three-dimensional space, what can I say about the direction of field? One wire which is coming from top, I know his contribution is clear. Now just take these wires and think about the contribution. And take it cone by cone. It will be very easy to think. So wherever you are, you can cut a ring in the horizontal plane and you have got a sphere down. You can take two wires which are making a V shape this way, whichever is comfortable, but with respect to that point of symmetry. Matlab, समझ गया? So this should be your new line of symmetry. So I think you understand it. ये line होना चाहिए और इसके respect में दो करके देखो, मतलब V with respect to that, V with respect to that, and then you can talk about the direction of field because of any two. So you got my point, huh? So अगर मैं general बात बोलता कि I have got this wire, I have got this extended wire, whichever way it is, and I am somewhere on the line of symmetry, and I am talking about the field. So the net direction there is very clear. बात समझ में आ रहा है? तो जो भी उसका डायरेक्शन है, that has to be normal with respect to the plane. ये तो मैं 2D करके दिखा रहा हूँ. For all these directions which will rotate there, they are always following the symmetry which I have taken. Okay, exact value to I have calculated from Ampere's circuit law, but the symmetric direction which I have taken is correct, which makes the problem easy. I'll try to just show you this pattern which is there in a standard problem also. Maybe that will help you out more. This is a previous question of standard text also. So just take this problem to, I'll share that with you. But the basic point in such problems is to observe the direction because of symmetric current carrying elements. Or if direction ka idea lag jaye, then it is very simple to apply the Ampere's circuit law. Now, one problem I have taken in between, which is based on magnetic field again, where I want all of you to use transformation and solve it in minimal effort. Again, there are two ways of analyzing this problem. The question is somewhat like this, that if you take a charge particle here, or t is equal to 0 पर इसको rest पे छोड़ दें, and let it slide on the surface for some distance L, magnetic field is cross direction, gravity is downward G. So we understand that as his velocity will increase, he will have a tendency to leave the surface. And obviously, starting from rest, when it acquires a speed V such that QVB equals mg cos theta, it leaves the surface. Because, I mean, this is the point where normal reaction will become 0 if mg cos theta of this particle is balanced by this guy, which is QVB, right? Direction clear hai, simple. QV cross B and mg cos theta. mg sin theta is accelerating this downward, fine. So यहाँ contact छूट गया, पहली चीज है. Now comes the, and second, by energy we understand V should be equal to root of 2as. So 2g sin theta multiplied by L. Work energy theorem. No work done by magnetic force. यहाँ तक सब ठीक है? Now comes the real part of the problem. Now what he says is, when it comes out, it moves under gravity and B is present. So what I would have done in this problem is, I would have myself gone into a frame which is moving, running. This guy is running rightwards with a velocity of V cos theta, I suppose. Yeah, V cos theta. Because immediately as he does this, he starts running with V cos theta, such that the effect of mg is cancelled. From his frame, the E will change, and the new E, you know that the new electric field which will come will be the previous one, which was nothing in this problem, plus an additional term of V cross B. This is the additional term because of transformation of field, V cross B term. So obviously, I told you the E new vector will be this. Thing like this, that proof is not required at this stage. So E old was 0 in this problem, and an additional V cross B. V is the velocity of the observer who is running here. So if he is running rightward and B is this old B, because B doesn't change, उसका जो changing term है उसमें denominator में C square है, so that term is irrelevant. So I mean, this will be this is the V observer. So V cross B will be vertically upwards, and that is Q. I mean QE जब लगेगा तो Q V cos theta into B आ जाएगा. And my interest is, now this is the force that I'm writing, forces which I'm writing, and there will be a gravity also everywhere. So these two will keep on cancelling is what is my interest. So बस एक field रह जाएगी, which is the original B. E will become this. So E old is 0, this new will come. This will, if this cancels mg everywhere, then mg is not there. And from my frame of reference, from his frame of reference, who is running with V cos theta, this guy has only one velocity, which is downward V sin theta. और V sin theta की velocity को cross direction में B में फेंक दिया, so it will start moving on a circular path. Just make it again. I mean, it cannot go below this point. I mean, this, you're gonna draw this again. It's like a circle, which is this, and the lowest point and the highest point of the circle will match up with the lowest and the highest here. The lowest and the highest there. Let's stop. Yeah. So once he starts moving from that point, what I wanted to say is, it will have a uniform circular motion whose radii is this, but the diameter of this, according to the problem, is h. क्योंकि उसके फ्रेम से यही दिख रहा है ना. We know that from Earth it will be cycloid. So that circular motion has got, and that dia is twice of radius, and radius is mv upon qb, and v now from this frame is mv sine theta upon qb. Now, if this is my third equation, it should be simple. And his question was to find out L. आपको L निकालना था, and the only thing given in the problem, I suppose, was H. H was given and theta. It is L in terms of, everything cancels actually, in terms of H and theta. So just use all these equations and eliminate all the possible terms. Let's see what will come. So I'll solve it here. You can also try to write the terms. So check what are we getting. चलो H का equation लिखते हैं. So it comes out as I have got mg upon qb. Theta I want to keep. So m upon qb term. So 2v m upon qb is v upon g cos theta. So v upon g cos theta and a sine theta here. And v square now is 2gl sine theta. Now I am done. This is 2gl sine theta. This becomes 4l. What are we getting? H का वैल्यू क्या निकल के आ रहा है? V स्क्वायर टर्म आ रहा था 2gl sin थीटा, है ना? तो 4l I am getting, and sin square theta term I am getting, and a cos theta term also we are getting. QVB cos theta term is equal to mg. Remember that. while you have balanced the forces, right? और h का वैल्यू ट्वाइस ऑफ एम वी साइन थीटा अपॉन क्यू बी है. अब एक बार कैलकुलेशन पूरा देख लो. v टर्म आई हैव रिटर्न m अपॉन क्यू बी. m अपॉन क्यू बी जब लिखा है तो v अपॉन cos थीटा टर्म लिखा है. सो जस्ट चेक द कैलकुलेशन. You solve it correctly. I'll write the equations. V is root 2gl sin theta. QVB को रख दिया mg cos theta. Q v cos theta into b. That I have written as mg. Now let me write the expression of h. It is 2 mv upon qb term, and a sin theta term is coming, which is v square upon 2gl. Just try to, I'll just write it carefully here. Just solve the calculation should be. कुछ हट गया क्या previously? You substitute the data, you should get the result. करो एक बार बनाओ. Let me write it this way. So h, I'm writing, my h comes out as twice of mv upon qb, and v का एक टर्म आ रहा था sin theta. So I have written sin theta as v square. Just observe my steps. मैंने इसको v square upon 2gl लिखा है from the second equation. So I got it as mv cube. This 2 will cancel out. I got it as mv cube upon qb gl term, और sin theta का टर्म भी आएगा. You got it ना? एक cos theta टर्म आ रहा है, तो यहाँ पर एक L का cos theta टर्म आ रहा है मेरा. mv cube upon qb gl cos theta is what I am getting. Check. H I am getting as mv cube in upon qb gl cos theta, and then I substituted all the terms carefully. This term became v4 upon g square cos square theta multiplied by L. And then when I have written h, it became 4. When I have written h, it became 4 g square L square sine square theta. Just look into the calculation. And denominator became g square L cos square theta. Everything cancelled. From here, my h came out as 4L tan square theta. थोड़ा सा ठीक से अरेंज किया तो L became h cot square theta divided by 4. And just you have to arrange those equations properly. ठीक से उनको arrange करो, so you should get yours. The point in the problem was only this thing, that when you are writing in the beginning, you try to get into a field from where one constant force mg cancels out. Rest magnetic field will stay, and from your frame of reference, velocity will also change, which will be responsible for the uniform circular motion. One more problem. Calculations you people can do. We'll pick up another combination for the day. Just look into this configuration. It's going back around. Again, it is from NADEG. A very relevant JEE advanced problem. काफी formats इसके अपने अलग अलग जगह देखे होंगे. Just try to write it once. Problem is saying, problem says there are two identical very long cylindrical conductors of diameter d and negligible resistance. They are placed parallel to each other with their axis separated by capital D, which is 50 D. Some calculation is also there, so be careful. एक्सेस दोनों सिलेंडर्स की इतने पे हैं. Now there is a battery of EMF V which is connected between the left hand ends of the wire is shown, while a resistor with resistance capital R is connected across the other ends. You have to find the resistance capital R that makes the electric and the magnetic forces between the conductors equal. Resistance की किस value पर electric or magnetic forces will be equal, that is what we have to find out. Now, right, I'm more interested in the expression of the electric force. Basically, what will happen is when you will connect a battery, initially the charge flow will be such that some charge will stagnate itself on the curved surface area of the two conductors. Or that charge will generate the field. अच्छा कुछ बच्चे ने पूछा बात इन जनरल. Okay. I'll discuss with the students who are writing on the chat box. So अब ध्यान से समझना कि he wants the easier part of the problem is to write the magnetic force, which is simple. The complicated thing is to understand that when the charge will flow initially, some charge will stagnate or will be present in an electrostatic manner on the curved surface area of both the conductors. Now, that charge should be such that it produces or compensates the potential difference provided by the external battery. उस चार्ज की अपनी जो इलेक्ट्रिक फील्ड हो उसका पोटेंशियल ड्रॉप दोनों सरफेसेस के बीच में V आना चाहिए. You getting the point? Then it will become simple. भाई, the basic thing is when a charge starts flowing, दोनों चीजें हो रहा है ना, something will flow, something will stagnate. तो कब तक वो जानना चाहता है कि what is the value of resistance such that electric and magnetic forces become equal. Now try to write the expression of the lambda, the electrostatic charge ka lambda on both the bodies. Very important. So let's write that. लिखना. The 2k lambda by r, तो मैं कुछ ऐसा ही सोच रहा हूं कि अगर इसके सरफेस के ऊपर प्लस लैम्डा आ जाए, मतलब this is apparent lambda, right? Actually there will be sigma and this surface has got a minus lambda. Write the field at a general r and try to write the potential drop. लिखना पूरा. Yeah, we could say, I mean, if I am located at this point, jiska distance from the axis of one of the conductors is small r, I knew that the field will be axially symmetric and radially outwards, not writing it. I mean, that E as function of r will be 2k lambda divided by r. Simple. So my idea was simple, that if I multiply it by dr, and I integrate it from the surface of first guy, so that is r is equal to capital D by 2, I mean capital D by 2 to r is equal to, what was that? Small d. अच्छा. R is equal to small d by 2 से कर देता हूँ, from the surface of one guy to the surface. So capital D minus small d by 2, I will have a potential drop which is actually equal to V by 2. That is my equation number 1. दूसरे का इतना ही सपोर्टिंग होगा, जिसका मतलब minus lambda will also contribute the same. The contribution of plus lambda from this point to this point and minus lambda same, तो मैंने सीधे lambda by V by 2. Now it is more about substituting the limits properly. So I'll have a 2k lambda ln of, it is d minus d by 2 upon small d by 2 ka. So this much I got. that becomes equal to, because ये value तो आ जाएगी, this comes out as approximately 2k lambda ln of 2 capital D by D type का term है. So I'm just, minus 1 mod. So approximately 2k lambda ln 2 capital D by D. Now leave this term separate and now start thinking. This is your first equation. 2k lambda. If I start writing sigma, that will be what? Like if I want to write lambda term, that should be equal to sigma, the charge density that I would have taken, into 2 pi d by 2 into 1. So basically, I can write sigma pi small d as lambda. Matlab, if anybody is interested, he can definitely put sigma down. Right? So in that sense, this expression will be 2 into 1 upon 4 pi epsilon naught into lambda, which is sigma pi small d ln 2 capital D upon small d. So pi 2 term. So sigma small d by 2 epsilon naught ln 2 capital D by small d. Sigma small d by 2 epsilon naught ln of 2 capital D by small d. That's fine. So यहाँ से sigma या lambda, whatever it is, that you will have. Now try to write. अब सारी चीजें भी छोड़ दो. एक बार F इलेक्ट्रिक लिखने का कोशिश करना. So let me write an expression of electrostatic force, and let me analyze everything per unit length. So keep lambda magnitude, and I'm talking about the magnitude of that electric force. So lambda आ गया per unit length into field. So I think we will write, because D is large, so it is 2k lambda divided by capital D. 2k lambda by. Now I think things are getting in place, because अब आप सिग्मा के टर्म में मत लिख के ऐसे लिख लो, जस्ट खत्म करना है, दोनों सही है. So it is 2k lambda square upon capital D. That is my equation number 1. ठीक है? And I think you also know the value of lambda now. Lambda is a known thing for you. If this is equation number 2, that was first. एक और लिख दो. So I want to write the expression of magnetic force now. And I'm writing per unit length again. So basically mu naught I1, I2 is I square upon 2 pi into distance between them, which is capital D. And everything fine. Resistance, और तो कोई resistance था नहीं. तो मुझे लगता है ये अब तो simple है. Mu naught upon 2 pi capital D. And now I can write that as voltage upon resistance, the whole square. Now it is more about elimination. Fm you can replace by Fe. Fe will have a lambda square term here. Lambda you should replace in terms of V. And then finally the unknown R should be solved. That should give you the result. Yeah, it should come out. Length, I don't think L term should picturize finally. Are L. L नहीं आना चाहिए. Cancel हो जाए. Answer should be independent of the length. So my analysis is fine. Per unit length I will get back. It is only solving equations. You will get it. So that idea of cylindrical capacitor also can be used whichever way you are comfortable. I could have directly used that thing also. मैंने लिखा integrate करके, but I was thinking कि if I was having plus lambda and I forget minus lambda by superposition, then I know the radius small d by 2 and I'm going up to this radius. The potential drop can be directly written as charge upon capacitance, and I'm writing per unit length. So I can avoid integral. I could have written lambda upon capacitance per unit length. And capacitance per unit length is 2 pi epsilon naught upon ln of R2 upon R1. So that is one line problem. You can avoid all those things and directly write the expression. I was just analytical in this. So I'll finish off the class now and we will pick up more combinations tomorrow. So take care.